My name is Mikey Vlahinos. Today's video will be a walkthrough of the concepts and steps utilized to help generate and reshape your geometry based
on CFD fields, or any field really, for flow or shape optimization.
So what does the process look like? We'll start off with an initial analysis. This can be anything from an oversized design space, or it could be more confined, let's say the interior of a cylindrical pipe. After the analysis, we export the desired output variables from our CFD software. This can be pressure, velocity, stress, heat flux, turbulence, anything available to us. Bring it into N-topology, in this case as a CSV file. We transform this data set into an implicit field that can begin to influence our design. We truncate this data set, let's say by removing regions of low velocity or pressure. We then generate and mesh a three-dimensional representation of this reshaped field. This new geometry, informed by our CFD, is then reevaluated either for continued iterations or eventually a final validation and verification. Our goal is to utilize CFD early in the design process. As mentioned previously, we effectively start off with a CFD analysis. We export the desired output variables into N-topology, and in this case, I've created a custom block or workflow that reads the data in and will immediately start to generate an implicit body once the predefined inputs are satisfied. At this point, we have our new shape or fluid domain. We then clean up the geometry, Boolean union it as needed to whatever other fluid domains exist, mesh the geometry, and send it back to ANSYS for continued iterations.
As always, with any custom block, you can open it up and see what's under the hood and ultimately what makes each of these unique and run. In this case, I tried to be pretty meticulous on the changes I made through each revision. So moving from 2.0 to 3.0, and ultimately in this case, looking at version 4.0. The same will be true for version 5.0 and 5.1. Each iteration, the description of the block, the description of the inputs, and the edit logs get more refined. The velocity field that we see on screen is a simple U-bend, inlet on the left, outlet on the right. For whatever reason, we have an obstruction or obstacle that defines our keep out zone. And so what we want to do is figure out what shape will most efficiently get our fluid there, whether that's reducing the pressure drop, improving the flow, etc. What we'll end up doing is truncating the shape based on the values that we want to keep or remove, and ultimately generate a new body based on these fields and results. Before I proceed, I'm going to set the upper and lower bounds of this field to the upper and lower bounds that we're going to mostly focus on today. So 0.3 to 1.3. Broken version 4.0 into three main sections: field definition steps, smoothing field steps, and meshing steps. We still point to the point map. We define our interpolation and extrapolation in nearly every scenario. The interpolation will be set at barycentric and the extrapolation set to none. We define our upper and lower bounds. A new value that we have is this resolution. This I'll explain a little bit more when I get to versions 5.1, but this ultimately will allow users to better shape the structure to capture the detail within the bounds or edges of that point map. So the blue here that we see is the outline of the point map, and that nearly is identical or in line with the implicit body that gets generated. Next input is the grid size. This is ultimately, you can think of them as the building blocks that create this implicit body. And this is, I'll say, directly tied to the tolerance value that we want the mesh to be built from. So I almost always tie these two together. They're equivalent in my mind. And the value for this smoothing grid size is generally going to be, at least the starting value, 30% of the mesh size that you use to run your analysis. Not necessarily the mesh size of the boundary layers, but the overall average mesh size. And I'll explain why that is a little bit more when we get to the build and tolerance size. The next two inputs, the smoothing iterations and interpolation types, are just used to smooth the field. But ultimately, once we generate this object and we're ready to compute, we click this check mark, and at the end, we have to do one final smoothing operation to do exactly as that block says, smoothing it out. The grid size in this case is generally going to be 3 to 4x of our smoothing grid or tolerance value. And in most scenarios, our smoothing iteration and interpolation type are going to be 1 in cubic. And so we can do a quick cross-sectional view here, and we'll see that we've captured pretty well the values on the outside bounds of our point map. But what we haven't captured are the upper bounds. So if we turn off the implicit, we can kind of see in here that we filtered out some of these high velocity regions. So we should expect to see some voids within this implicit body that we're ultimately creating. Versions 5.0 and 5.1 of this block have been revised within the custom block and do just that. So we'll turn on 5.0 here, and you'll notice that there are fewer inputs than with 4.1. I've removed the interpolation and extrapolation within the field definition. Again, those really aren't going to change from the barycentric and none for extrapolation. They're still within the compound block, so if you need to access those and pull them out for yourself, by all means, they're still there. The resolution value, the grid size, smooth iteration, everything else is still here. Just those two values have been removed. This still produces a little bit of a chunky, we can call it looking implicit body. So again, one final smoothing step is going to be required, and it's the same inputs and definition. So about 3 to 4x our grid size, 1 in cubic for the interpolation. Right away, we can now see that we're filtering out these regions where we have high velocity. So if we do our cross-sectional view, we do indeed see that we have these void regions within the body that have now been pulled out. Version 5.1 has the smoothing process built into it, and I've also removed a few inputs as well as combined them. So for instance, the build and tolerance sides have been put into one. That's just going to be, if we open up 5.0, that's going to be our grid size, and our tolerance are now called build and tolerance size. I've also removed the smoothing iterations and interpolation of the initial point map to field algorithm that happens within the compound block. I've left those at 1 in linear. In the studies that I've done, in the feedback that I've received, that has seemed to be the primary direction that most users take this. Again, those are still available for whatever reason. There's a new section at the bottom that is called final smoothing, and that's simply just this final smoothing body step where we have our grid size defined, smooth iteration, and interpolation type. Again, this grid size is going to be 3 to 5x our build tolerance, and these won't stay, these should stay the same at 1 in cubic. And then when we're ready to generate, we click this check mark, and the body will get computed and ultimately built. So again, we can look at our cross section And what we've done is really just taken that last smoothen operation and put it into this block as a whole. So let's talk a little bit about the nuances of the inputs. We'll start with the resolution, talk about the build tolerance, and continue from there. So looking at the resolution, really what we want to do when we're working with this block and these fields is we want to create an implicit body that represents, if we turn on the one we were just looking at, that represents and stays within the bounds of our point field. So we're going to go through 4 different examples here where I'm changing this resolution value and going to continue to decrease it. It needs to be, if we look at the properties tab and go under the inputs, I've put a lot of detail and effort into trying to best describe how to approach each of these values. And for instance, this resolution value needs to be less than 1.0 and greater than 0.0. So this resolution is set to 0.5. And if we turn this on, we'll see that we're not capturing as much detail of the object that we want. We still get a nice smoothed body, but we're really, not capturing anywhere near what we would expect or want. So we can continue to decrease this resolution value. We'll take it to 0.1 now. We're doing a little bit better. We've captured more, but we're still missing some of these top sections and the ears, especially on this structure. Continue to decrease that. And eventually we'll capture more and more detail. We're seeing that we have this pocket now. And finally, if we go to a value of 0001, which is an order of magnitude less than the first version we were looking at here, we'll see that this pocket kind of closes and that we've really captured the details of this ear. Now we know that we really won't want these ears present in our analysis or our final model, I should say, and they would get filtered out in the next iteration when we continue to truncate these values. But if we look now at a cross section of this, we can see that even though we've captured this little bit of extra resolution, we don't necessarily have a lot of flow area for our fluid to move through in this little pocketed region. So we might make the argument that the resolution that we have with the 0.001 is sufficient. The block will run a little bit quicker, so we can iterate and get to production that much quicker. Moving on, we'll look at the build and tolerance size. So what is the build and tolerance size? We'll take a step back and remember we're bringing in a set of points, and these points correspond to nodal locations within our analyses. So that being said, we know that we have elements that define certain volumes within our point space. And this build size effectively says how many building blocks, we can call them, or how many smaller elements do we want to fit inside and interpolate between these. So a value, a build tolerance value about 30%, the size of our elements will give us roughly 3 building blocks within each element. If we go to a build or tolerance size equal to or greater than our element size, then we're going to get a very blocky looking implicit at the end because we're not fitting within the bounds of our mesh as it's coming in. The other aspect to this is the time that it's going to take the block to solve. Because remember, the build size that we use to create the implicit is going to be equivalent to the measure tolerance size that we use to clean the implicit field up with. So for instance, if we look at this guy, we can see that at a build tolerance of 0.6, it's much more blocky and less accurate than if we go back to our builder tolerance size, where we have a value about 30% of our element size. Now we can continue to refine this value indefinitely, right? We can say, well, I want to have, I don't know, 5 times or 6 times as many elements within building blocks within that element. And we will indeed get more resolution. So the red is the value, has a build tolerance value of 0.075, so half that of the gray object that we're looking at. And we'll see as we do a cross-sectional view, in some areas, and especially when we get to these windows here, we are capturing more resolution, but at what cost? In this case, this block ran 91%. It took 91% longer to compute than having a build tolerance size of 0.15. So at least during the iterative process, again, we need to find that balance between the fidelity that we want and the time that we want to spend computing. So I mentioned that the build and tolerance size is related to the building blocks that we put within our elements. Now, in this case, once we get to the bounds, this value is significantly larger than what we want to capture. And that's where this resolution value comes in. So we have the build and tolerance for ultimately capturing the detail within our large solid body. And then we have the resolution value that lets us fine tune the outsides or insides where we have and want tighter control. Last 2 aspects I want to touch on are filtering and then the smooth and body operation. If we want to still focus on certain sections, let's say the inlet or outlet regions, then heat exchanger, we're still able to do that simply by using any implicit body and intersecting it with that field. We can define whether we want to keep the region inside or outside, and in this case, we'll keep the values for the point cloud within that region, and then we can use this new set of points as our input for our implicit body generation. Last little bit of iterating that will be required is going to be in the smoothen body block. So again, this is built into 5.1. And what's going to end up happening is we will ultimately need to adjust this grid size until we have hit our target value. In the handful of studies that I've done, that value of 3 to 4x our build and tolerance size seem to work pretty well. So this is a grid size that matches the build and tolerance, and we can continue to increase this, further refining the smoothened body. And the best way to really approach this is to have our point map or point cloud turned on, and we can just physically check to make sure that we're within those bounds. And if we get too small or too large, we'll start to remove away and reduce the fidelity that we ultimately want to keep in capture. So again, value of 3 to 4x the build or tolerance size seems to work pretty well. Last thing I'll show you is this real time, just so we're able to see how quickly this ultimately runs. So in this case, I'll just delete this lower bound. I'll unclick the ready to generate, and we'll drag and drop the lower bound into here. We'll click generate, and we'll see in a few moments that the block gets created. So once we have our parameters set, the resolution, the build tolerance, our grid size, that really shouldn't change for the specific problem that we're trying to solve.
We'll do a deeper dive into the inner workings of both the field from fluid domain 4.0 and 5.0 and 5.1 blocks. This starts with an imported CSV point map, and it comes in unitless. All that we bring in are the magnitudes at each of the nodal locations. The units defined here are purely for scaling the object. So if I Control C, Control V, and maybe set this to centimeters, and then zoom in by pressing Z, we'll see that we have a scaled down size of this object. The scalar input here is where we would define the units if we want to. In this case, it would be meters per second or whatever data set you're bringing in. But ultimately, we're going to turn this into assign distance field, so we'll eventually just assign units of length. So I leave the scale option blank. We take this point map, and for the most part, the process that I talked through on 4.1 here on the left will apply to 5.0. The only difference will be in this ramp clamp variable, which I'll touch on later. We'll take this point map, turn it into an implicit field using field from point map. Again, our interpolation, because we're bringing in a mesh, is going to be barycentric, and the extrapolation is going to be set to none. If we hit F and look at the field viewer, set turbo so we can see some color. We don't really care what the outside is going to look like. We're only wanting to reshape the interior, so we'll leave that extrapolation set to none. In both of these files, under either the interpolation or extrapolation, you can access a support article that talks more about both of those inputs and how they impact your overall outcome with this block. The next step is using this clamp block. This will ultimately define the regions that we want to truncate. So again, the field we're viewing is just of this initial field from point map. And what I'll do now is turn on the point map, go ahead and set our bound 0.3 to 1.3 meters per second. So that's ultimately the shape we're going to get, the one there that we see on the right effectively. So when we use this clamp, when we define our lower and upper bounds, all we're going to say is everything that is below or above those values, you're going to keep as 0.3 in this case, or once we get to our high values that are higher than 1.3, they'll be defined as 1.3. Everything in between is going to stay the same. The next block or step is where most of this workflow really is, and the same will be true for versions 5 as well. So what we need to do in order to generate an implicit body is have negative values, 0, which defines the boundary, and positive values, which defines our empty space. So again, in the implicit world, negative is our geometry, 0 is the boundary, everything positive is empty space. So if we look at the field here, the clamp CSV, everything is positive. So if we were to try and visualize this, we would not get anything on the screen. So we need a way to turn the values that we want into negative value and leave everything else as a positive while having a transition zone. This ramp is used to do just that. The input field is that clamped value that we previously created in step 2. And the in-min and in-max in this case are going to be the lower and upper bounds. So where we have our lower bound, we're going to define that resolution value. We put a small value here, 0.001, or anything really between 0 and 1, so that we get a fine gradient. If we would to put 0 and try to visualize the field, it would look a little bit wonky. The upper bound then is going to be defined as our negative value. So if we were to then visualize this field, what we're saying is everywhere that we have our lower bounds, everywhere that we're outside of our object, we're now going to be a positive value. And then we're going to transition to -1 on the inside as we get to that max value. So again, if we look at the clamp CSV, we're 0.3 out here, and we're going to say everywhere that's 0.3, we're going to assign that resolution value, which in this example is 0.001 millimeters. And everywhere that we have our upper bound, you'll eventually transition to a value of -1. So here's our 1.3. We'll evaluate and view this field, and we have -1. The next aspect is simply just multiplying this back to the clamped CSV. This is going to give us our gradients and values back to us. So all that's going to happen here is now we have -1.3 on the inside versus a positive 1.3, and we'll transition down to our low value at the end. We're still not quite able to visualize this. The reason being is if we go to visualize this block in specific by toggling the visibility option here, we're going to see an infinite sized field because we've not confined it to any particular space. I can show you that by increasing the size of our field viewer, so we can take this out to 500, for example, and the object that we're most concerned about doesn't change, but again, this positive field is just going to extend to infinity. So we need a way to confine that, and we'll use the set bounding box block to do that. The bounding box that we'll use is that of our CSV point map. So we can right click, say go to block, and under properties we're going to use this bounding box, and I'll just pull it out so we can see what that looks like. So now we're going to confine this field that we've created to this bounding box. Remove that, and now we can visualize this. We won't see anything too spectacular, but again, we're going to be confined to this smaller space. Similar to what we had seen on version 3.0, we don't really get a good idea of what the geometry is going to be represented. Like we could do Control H to better represent what that's going to be, but again, there's no point. We can clean it up later on. So the next step is to smoothen this field out. This is going to be our grid size. Again, smoothen iteration and interpolation type. I won't go into how those impact the outcome. We'll visualize this, and we'll get a little chunky block at the output. At this point, the next step in order to clean this field up or remove this exterior bounding box view will be to mesh the object. In order to mesh it, we want an implicit body, so we can come under the properties of this smoothen field, extract the implicit body from here. That's simply just dragged onto the notebook and then as an input into this mesh from implicit body. I have the tolerance value extracted as a variable and an if statement that will either multiply the input tolerance by 0 or 1, whether or not this ready to mesh is selected. Value of 0, the block won't solve. Any value above 0 and the block will compute and we'll get a mesh out. So this removes that exterior negative exterior field. And then the last step is just turning this into an implicit. And 4.0, the smoothen body step is not included in the workflow. So outside of this custom blocker workflow, one extra step would be needed to smoothen this field to get our final desired shape. Now if we take a couple steps back and look at our CSV point map here, I'll increase the upper bounds. We see that we have a lot of red data points inside. And as we start to pull this down or go to our upper bounds of 1.3, we would expect to see some voids inside of our final implicit body. So we can isolate this, do a cross section, and unfortunately with versions 4.0 and below, we are not truncating out that inner volume. Exterior upper bounds will get removed with versions 4.0, but again we're missing that interior removal if that's so desired. Version 5.0 and 5.1 address that. The only difference in this workflow really comes down to this ramp clamp value. So I'm going to minimize some of these blocks here on the left and just leave the ramp clamp here of version 4.0 up. So it's a little bit more complicated. It's got a ramp block nested within another ramp. And you might notice that I've had to swap the upper and lower bounds in the in-min and in-max values of the original ramp. Good way to visualize this will be comparing the fields of both the versions from 4.0 and 5.0 and 1. So I'll turn off the implicit body in 4.0. We can visualize the initial ramp field, probe these values, and do the same thing for this ramp before we multiply it back to the CSV. And put turbo on. So we can see on the left is where we are not able to capture the inner volumes and remove them. In order to achieve that, I had to flip the in-min and in-max values. So where I have my in-min, I'm defining that as my upper bound, and my in-max will be defined as my lower bound. The out-min that's assigned to this upper bound is defined by another ramp. And so I'm saying my in-min and in-max for this case are going to be both the upper bound, and I want you to transition from -1 to 0. The lower bound then is still tied to this resolution, so we're going to be transitioning from -1 to 0 to positive within this ramped ramp. And visually there on the right, we can see what is happening. So we have positive value out here. This is going to be empty space. We're transitioning to a negative sign distance field, which will be our implicit, and back to 0 in this case, where we're going to have geometry ultimately removed from that implicit. And we can turn on this point map, and I should already have it preset to the lower bound here in this case being 1.3. So 1.3 and above, everything is going to be removed from the implicit body that gets generated. And we can see how that
this point cloud then fits into this field. And if we draw this up and toggle off the visibility of the point map, we'll see that we have this interior space ultimately removed. Again, then we just multiply this back to our clamped CSV to give it a better gradient and reassign some normal values to it. Ultimately then, what happens, the same steps that we previously went through, a smoothen body, we'll turn off the field viewer, look at our cross section, and we have that interior volume removed from the design space. There will be times when I think customers will want to use versions 4.0. It's still great and will still do its job. You just won't have the interior structures removed. And at times where you would want to use 5.0 instead, so you can get internal cavities removed, whether they are high or low bounds with regards to how you want to truncate your design space.